Welcome to lecture number 4 of module 2. In lecture 3 we saw the capability curve of synchronous alternators, and also we saw the various transformers and their uses in electric power system. In this lecture I will discuss about the capability of transmission line. So before going to see the capability of the transmission line, it is important to see the various transmission lines, means in terms of their length and what are the various representation, so that we can discuss in detail. A transmission line, as you know, it has resistance, it has inductance, it has a capacitances, and all these parameters are distributed in nature. If you see this single line diagram, where this I have written, this is R is the resistance, and again this is in per ohm per kilometer. Means it is a once length is keep on increasing, the resistance is also increasing. Similarly, the inductance of this circuit of this transmission line, and the inductances are formed because we are having the different phases, and then there will be current is flowing of the different magnitude, and due to that the flux magnetic flux is produced, and then we have the inductances. Similarly, we have the capacitances because the conductors are charged at the different potentials, so there are some capacitances are formed, and it is a throughout the transmission line length. So this is the capacitance, and that can be calculated using the different formulas, a different concept. Again we can calculate using the GMD and GMR concepts. Another term is also associated in the transmission line distributed parameter, that is your G, and this is called the conductance. This is representing a resistance, means it is a loss component, and this loss component basically represents because we are having the insulators. And why we require the insulators? Because the bare conductors are hanged over this towers with the help of the your insulators, and there will be some leakage currents which will be flowing on the surface of insulators, and there will be some loss. So it is also distributed because the towers are distributed throughout this length of the line. So this G is also a distributed parameter, but for analysis purpose we normally go for the different representation for the different line, and then we can classify the lines depends upon the length. First one is your SART line. SART line is the line which length is less than 80 kilometer, or you can say 60 miles. In that case, what we normally do, the charging, that is a C and G here, the charging capacitance as well as here the conductance is ignored, and only we take the series impedance, and that impedance is represented here as a lumped parameter. Means here it is Z, it is your R, capital R I am writing here, your omega, this I am writing this L. So this is basically in ohm or in per unit, but it is not per kilometer because we multiply by the length. So this is the lumped parameter, means this resistance here as well as the here the reactance due to the inductance, it is the complete of the total transmission line. So if it is a per kilometer, then you have to multiply by the length of the line. Another category is your medium line. Medium line normally represents from 80 kilometers to it is 160 kilometers, and in some cases it's up to 200 kilometers. Its analysis is performed using concept of the medium line. In the medium line also we normally represent the distributed parameters in terms of the lumped parameters, means we have to lump the total series impedances or this your shunt admittances, but here in this case we cannot ignore this charging capacitances, means we cannot ignore the capacitance value, and that's why we include here this Y in this formulation. So again we can lump, now you know this shunt part is distributed. So this shunt can come in the intermediate of the line, it can come at the both end of the line. If here it is represented in the intermediate of the line, you will see this is called the T representation, and it is called nominal T because here we have made some assumptions. It is not equivalent T. I will discuss equivalent T here in the long transmission line. So this you can see just like a T here, and that's why it is called nominal T representation. Similarly, we can also, now if you are the shunt admittances, if you will separate half of the separately, here one end, here another end, and the series impedance here, the complete, is lumped in the between, then it is called nominal pi representation. And then we can go for the various analysis, and now this calculation becomes very simple. Now what are the various calculations? Normally we go for calculating the performance of the transmission line, and the performance of the transmission line is defined as the here the voltage regulation, and another is your efficiency of the transmission line. So we can calculate the losses in the transmission line, we can calculate this your sending end voltage, receiving end voltage, and then we can calculate the regulation. However, in the long transmission line, if your line length is more than 160 kilometers, in some cases 200 kilometers, then it is not possible to take the lumped parameter, and that calculation becomes very erroneous. So what we do, we go for taking the distributed parameter, and using the distributed parameter concept, we can define the transmission lines in terms of their ABCD parameters. We can even go for the equivalent T and equivalent pi. Means here this is, you can see this is a T. What we do normally, if you would here, this is a T, of course, this is, we are taking here T, and we are now representing in terms of lumped, but taking the consideration of the distributed parameter. So here your Z prime, it is not here Z by 2 here, similarly here Z by 2, and here it is or Y prime. So this Y prime, Z prime are basically related with your distributed parameters. Here Z and Y are the lumped parameters, means that is multiplied. Similarly we can go for this pi representation, and that is called your equivalent pi, because what we are doing, this distributed parameter we have represented, and then we are trying to represent that line in terms of equivalent of pi, so that's why it is called equivalent pi. So here what we will get, instead of this we will get here here we can get this pi like this, this is your pi here, and here your Y by 2, this is a prime, here Y by 2 prime, and this is your Z prime again. So we have to represent in equivalent form, and then it is called the equivalent representation of the transmission, long transmission lines. Now the various constraints, various limits, those are imposed in the transmission line, and they are the restricting parameters that we have to look into the matter before transmitting the power. First one is the voltage limit. The voltage limit is nothing but related to your dielectric limit. The voltage regulation limit, that's how much change in the voltage from the full load to no load, that is also very important. Another is your stability limit, that is whether we can, how much power we can transmit over the transmission line without losing the stability of the system. Another is your thermal limits. Thermal limit again related to that, if you are keep on flowing more current, there will be some losses, and therefore what will happen, due to these losses there will be more sag and etc., and then we will see. So all these 4 limits we will see in the next few slides. To avoid several things here, especially the stability limits, we should go for the compensation of the line, and we will see the various compensation techniques also, and based on that we can improve the stability of the long transmission line. So let us see the thermal limit. So the transmission line thermal limit, the excessive temperature due to the loss. What is loss? If you are going for more current in the conductors, so there will be more current. More loading means more current, and if there are more current, then what will happen? I square R loss. R is the resistance, so I square R loss will be high, and that may result in the expansion, because there will be temperature rise, and the resultant sag of the conductor causing decreased clearance of the ground. What will happen normally, if you will see, this is your tower, let us suppose, and this is your transmission line, which is a form of the catenary. If the temperature will increase, what will happen? This will go like this, and if you are a ground here, then what will happen? Here the ground clearance is reduced, and there may be possibility of the flashover, there may be possibility of the human damage, and that is not required. So the excessive temperature rise due to the I square R loss normally limits your thermal limit. Now another question, why the temperature, excessive temperature? Once there will be loss, there are several conditions, that is it is the lines are hanging in the sky, in the you can say air, and always once the loss is there, it is dissipated in the air. But if the loss that is more than the dissipation of this loss, that heat. If less, then what will happen? There will keep on increasing the temperature of the conductor. Once it will keep on increasing, then we will have the sag, and that is the expansion, and the sag, that is very, very dangerous. The temperature extremes have an annealing effect, causing the reduced mechanical strength of aluminum. At the same time, it is not only sag, means if the temperature increases, then this has the annealing effect, means it will reduce the mechanical strength. Normally, we never use the simple aluminum or the copper conductors. We use basically different type of conductors like ACSR we use, that is a aluminum conductor steel reinforcement to give the more mechanical power strength of the conductor. But the aluminum which is used, normally we use the aluminum for the wire conductors, and the coppers are used in the cable because the aluminums are cheap, so aluminums are used. So here what will happen? It will reduce the excessive temperature, the strength of aluminum. Since the thermal time constant are large, no doubt the thermal time constant is very large, so it is useful to distinguish between the steady state and the transient thermal rating. Because the transient thermal ratings means if there is a sudden change, sudden increase of momentarily increase in the current, how much loss is there, so the temperature rise will be slow, it is not so instantaneously to be increasing. And another is steady state, that we can transmit the power without losing much sag and also without losing the mechanical strength of aluminum conductor. Thermal capability is a function. How much thermal capability of a conductor is basically depends upon the several factors, and one is very important, that is ambient temperature. What is the temperature outside? Especially if it is a cold weather, then you can go for more current because this heat dissipation will be more. Means outside temperature is also very important. Wind condition, because if wind is there, so this heat which is around the conductor, that is generated due to the current, that will be flowing, and that is a good way of the conduction of heat. Size of conductor means size whether it is very thin, very large. If size is larger, again the area will be more, and the more dissipation of heat will be there, again the temperature rise will be less. The conductor type, again the different type of materials are used, and those materials also what is their thermal resistivity, and based on that we can also decide what to be the temperature rise. Geometry and the spacing between the towers, means what is the towers, what is the geometry, the three conductors, because if there are the three conductors very close, then heat generated by these three conductors will come into the picture, and again there may be more rise. So if it is spacious, then again the cooling will be again better. Ground clearance is also very important, because the ground clearance, if there will be more temperature rise, the clearance will be reduced, and then therefore we cannot operate the line successfully. Typical steady state thermal specification of conductors used for 400 kV overhead transmission lines, the 400 kV just I am going to talk, it is for the Indian condition. This ACSR, as I mentioned, it is aluminum conductor steel reinforced. Means what we do, we use here the steel inside, and around this we use the aluminum conductors, and it is called, means there may be even though not only one layer of steel, it may be the one or two layer of steel, and over and above we can go for here the aluminum conductors. So normally this type of conductor is known as stranded conductors. Means here the conductors all are touching here just like here, and the equation for this, the number of conductors in any particular layer is basically given by n square minus 3n plus 1. Means if you are using 1, n is equal to 1 means only one conductor, that is in central conductor. If you are going for the two layers, then you will find here 7 conductors will be around that. Normally for 400 kV we use the twin Mohs, means we use the bundle conductor of Mohs, and that is a here conductor 520 square mm. Here the conductor area just I am talking 520 square mm normally used. One thing is very particular, you can note here the Mohs. Normally in this 50 Hz cycle, the conductors which are used, the name given are based on the animals. However, in the 60 Hz supply system, especially in USA and the Canada, they use the birds name. Like in India, this various conductor names, you can see this moose, panther, zebra, dog. So all these are the basically animals. and based on the MOOS, if you are any person is in the MOOS conductor, automatically the area is decided. So for 400 kV we use the two bundle conductors here. Always if you find most of the cases, you will see if the two conductors in one insulator it is flowing, then it is called the twin MOOS, and then it will be most probably 400 kV transmission line. So for an ambient temperature of 40 degrees Celsius and a maximum conductor temperature of 75 degrees, this ampacity is nothing but the ampere capacity, and that is approximately 700 ampere of this one conductor. Typically, as I said, the two MOOS conductors, that is the bundle conductors, is used in 400 kV line. Thus the total ampacity is twice of 700, that is your 1400 ampere for such a line. If a triple AC, that is all aluminum alloy conductor of again the same square area, that is 520 square mm is used, higher conductor temperatures are compared to the ACR are possible. For an ambient temperature of 40 degrees Celsius and maximum conductor temperature of 85 degrees Celsius, this ampacity is 850 ampere. So in our country mostly we are having the conductor of ACSR, or it may be this triple AC, and that is why the maximum temperature allowed here is 75 or 85. The thermal rating are a strong function of ambient condition. As I said, of course the ambient condition means outside condition. What is that? Means if there is a rainy season, whether it is a windy, whether it is a cold season or hot season, this thermal rating depends upon the seasonal and also you can say ambient condition, the condition outside the conductor. It makes sense to evaluate the actual ampacity during the real time operation, especially due to the season to season, day to day or hour to hour. So even though hour to hour also this varies, because in the night it may be the cold and the daytime it may be hot. So again the how much you can load, that depends upon the time to time, again hour to hour, day to day or season to season. Another limit is the dielectric limit, and that is basically nothing but the voltage limit. The exceeding the dielectric limit, maximum electric field strength results in the failure of insulation, causing faults. Electric fields may be excessive due to the various reasons. Reasons may be due to the over voltage, and that over voltage again may be of due to the two reasons. One due to the low loading condition or no loading condition in the AC transmission system, and that is called the Ferranti effect. I will discuss the Ferranti effect. Or during the abnormal conditions like the lightning strokes, or due to the faults. So we may observe the over voltages. As I discussed, the conductors in the transmission line, they are the bare conductors and they are hanged over the transmission line, and again the transmission line as well as the transmission towers, they are isolated with the help of the insulators. So these insulators must sustain the voltage that is your conductor is having, means your operating voltage will be withstood by the insulators. So we have a various type of insulators. Normally we use the string insulators for ESB transmission line, and again the utilization of these string insulators are not 100%, means the conductor which is near to the bare conductor is stressed highly compared to the conductor which is near to the tower. So let us see the Ferranti effect. The Ferranti effect is nothing but in the long transmission line or cable, the receiving end voltage is greater than the sending end voltage during the light load or no load. Means here your transmission line, this is your receiving end voltage, this is your sending end voltage. So during the light load or no load, light load means very less load, you can say negligible load, then this your VR, means magnitude of VR here will be more than what you are supplying and what you are connecting, and this is known as the Ferranti effect. Why it is so? And this is nothing but due to the charging of the transmission line. This phenomena is very prominent, very more in the long transmission line where the charging is very, very high. We can see again this effect by mathematically formulating this. The sending end voltage, this Vs, is equal to your receiving end voltage multiplied by cosine hyperbolic gamma L plus ZC, that is a characteristic impedance. Here your IR is receiving end current here IR, and here it is your IS and sine hyperbolic function. If your IR is 0, means if this current is 0 or very less, then we will have the VR, that is your sending end voltage, will be equal to your Vs, that is a, this is VR, sorry, this is the receiving end voltage, will be equal to your sending end voltage divided by cosine hyperbolic gamma L, and this value is always more than this VR, means this cos hyperbolic gamma 1 is greater less than unity, means your the VR will be more than the Vs. In this value can be unity because the gamma is very small value. So this value can be unity or it can be less than that. If it is unity, then it will be your VR, that is the receiving end voltage, will be equal to your sending end voltage. But for other cases, if transmission line is long, this value will be not unity and it will be less than that, and finally your receiving end voltage will follow this, and this is called Ferranti effect. Now this voltage, if it is higher, then how to control this? Because if voltage is very high, so there will be flashover over the insulators and this line will not sustain and the protective system will trip this line. So deviation of the voltage beyond certain limit can also be considered to be an unacceptable compromise on the quality of the power being supplied to the customer. If this voltage is, as I said, the voltage deviation is not allowed beyond the plus minus 10% in the most of the cases. In some of the cases it is not allowed more than plus minus 5%. Again, it depends upon the which voltage we are talking about. For the distribution system it may be 10%, that is allowable, but in the EHV system it should not be more than 5%. So if voltage is more, again there may be possibility that will damage the apparatus or equipments used by the customers, that is also not allowable. So we have to have some voltage limit, means voltage should not violate the limiting values, that is the lower limit as well as the higher limit. No doubt we know the higher limit will rupture the insulator, that will be the short circuit, there will be heating and so on and so forth, but at the same time the lower limit is also very important, and that basically relate with the reactive power requirement of the system, because if the voltage is low, what will happen, then for the same more reactive power will be requirement will be there, and there may be possibility the current in the conductor will increase and there will be more losses. So if the Ferranti effect is there, if a long transmission line is there, so what we do, we use some reactors to reduce, because the if your transmission line is energizing after the grid collapse, then the receiving end load is normally it is nil. So if you are connecting the sending end with the some supply system, then of course the receiving end voltage will be higher, and there will be possibility that your circuit breaker will be tripped due to the high voltage relay picked up. So what we do, we use the various type of reactors, and again we cannot put these reactors permanently for all the time. What will happen, because these reactors normally absorb the reactive power and therefore they will try to reduce the voltage. So sometimes we don't want that these reactors should be permanently connected to the line. So what we do, we go for the compromise, means some reactors are permanently connected, some reactors are connected when they are used, when they are required in the system. For example, this first one is a reactor, is your line reactor. If your transmission line is more than 250 kilometers, we use the line reactors, means our transmission lines here, let's suppose this is your transmission line and this is more than 250 kilometers, we use here reactors at the both end, and this is nothing but these reactors are your simply your inductor. So and they are permanently connected in the system, that's why they are called the line reactors. No doubt here we use the circuit breakers again for the protection and other, you can say, maintenance purposes, but they are always connected in the system, especially in the 400 kV transmission lines. If the line is more than 200 kilometers, we have to connect the line reactors at the both end of the line, unless until if you are, let's suppose you are having a generator here, that